Recording is on.
Awesome. I hope this is going to work. And let me welcome everyone to another session in our protocol study group, in our advanced sessions, this time focused again on Lean and specifically with O or Unnawut from Ream Labs, looking into the LeanSpec and the tooling around the Lean development. So we actually had a session from Colby, also working on Ream from a few weeks ago, where he looked into the client architecture. So we have some general idea in how the Lean works, but now more into the specification and the actual tooling behind the development process. So excited to have you here. Thank you so much again for joining. And if you folks have any questions, please use the comments here. Feel free to raise your hand, but we will take the time. You can just keep going. And I will get to the questions when there is some space later. So the stage is yours. Yeah.
Cool. Thanks, Mario. So hello, everyone. So my name is Unnawut. I also go by the nickname O. Long story short, all Thais have nicknames because their parents said it for them, and my name is O. And basically, it's because the Thai names are really long, even for Thais. It's really hard to pronounce, so everyone has a nickname since birth. And so mine is O. So you can call me either Unnawut or O. So currently I am working under Ream Labs. So I'm basically the coordinator, but also an engineer here. Mainly my work is a little bit different from Colby's, because Colby is working mostly on the actual implementation of the Ream client itself, while I am more focused towards specking and helping out with the specs and the testing of the overall, say, Lean consensus effort. So today, I am going to be cover pretty much like three objectives. So firstly, I'm going to be giving an overview of all the repositories related to PQ consensus. And then I'll deep dive into specifically the LeanSpec. And hopefully, like with these two things at the end of this session today, hopefully like we get to understand how the different components, like the Lean signature that Emil was presenting in EPS some weeks ago, also the Lean client and its architecture that Mario just mentioned, that Colby also talked about. This third part is going to be about the LeanSpec and also give an overview of how they work together. So without further ado, I want to kind of like show this kind of like overview of all the repositories, all the main meaty work that's going on inside PQ DevNet or Lean Consensus. And it's broken down into like kind of like 5 levels, from the kind of like high level on the left to like more like implementation and more of the tooling stuff on the right. So starting from coordination, we have the PM repo. I'm gonna go into like further details about each of these repo a bit later, but just an overview. So we have the coordination level, we have the PM repo. On the specifications level, we have 2 repos. We have the LeanSpec repo and the Lean metrics repo here. The third level is the kind of like what I would say like the shared implementations. So it's they are the implementations that are being used across multiple clients. And so those 2 are the Lean signature. And this is basically what Emil talked about a few weeks ago. And then we have the Lean multisig implementation, which Emil is also the main person working on this. But it's basically the aggregation of this Lean signature that Emil talked about. The next level after the shared implementations are the client implementations. So this is like all the client implementations in different languages, like Ream are implementing in Rust, Zeem is doing it in Zig, QLean is doing it in C++, I think, and so on and so on. And then the last level, we have the infrastructure and tooling, which are Lean Quick Start, basically the repo that we are using, containing all the Ansible scripts to start off a DevNet, either locally or remotely. And then we have more recently PQ DevNet Observatory, which is basically consuming all the metrics that are generated from the DevNet themselves and analyze them per DevNet into something that's more insightful and feedback back into next iteration of the development, right? So today we will be talking about all of these repos that we are pointing down, but the specific focus would be on the LeanSpec. Okay, so without further ado, I'll start off with the Lean PM. So the goal of this PM repository is to collect all the high-level documents encompassing each of the DevNet's goals and main changes that are happening per the DevNet level itself. Maybe I can go just by, see if this works. Maybe I can just open the website itself. Okay, wait, maybe one more sec. So I guess this might be a bit better for presentation. Yeah, so this is basically the PM repo, and the main focus that I think the main media content of this repo is inside this folder, inside PQ drop folder. And what you would find here are the README itself, of course, and then you see there's 4 documents, basically PQ DevNet 0, 1, 2, and 3. So these are basically the gradual changes that we apply to each of the DevNet. So I'll just go through like quickly. For example, like PQ DevNet 0, it was our first PQ DevNet. So what we did is we kind of created the repo, created the underlying framework, and the targets are pretty simple here. So we just basically want a network that has a slot duration of 4 seconds, using Quick as the network transport, using gossip sub. For consensus, we have been using 3SF mini, and the infrastructure for DevNet 0, we actually didn't have any remote like DevNets at all, right? So we just wanted to create this framework, have all the initial implementation set up, and try it locally, right? So what we're able to achieve for PQ DevNet 1, PQ DevNet 0 is basically the framework, the local infrastructures, and being able to test the clients. I think back then we had 3 clients, Ream, Zeem, and Clean, basically being able to finalize on the local machine. So once we did that in DevNet 0, in DevNet 1, we started adding post-quantum signatures only in DevNet 1, and that's basically the LeanSpec that Emil talked about a few weeks ago. And you can see here that in this document, it's mainly covering the existing stuff, and also adding stuff like native signature aggregation stuff. Right, so this is, I would say, like this document or these group of documents were actually useful for each of the clients who are following and trying to implement the DevNets up to the latest DevNets. They would actually focus on this specific documents, and they would see like a high-level overview of all the changes that they need to implement for each DevNet. DevNet 2, similarly, once we have the signature signing and verification set up, then we implemented Lean Logistic, which is basically the aggregation in DevNet 2. And then in DevNet 3, which is the one that we are focusing on right now, the implementation is already done, but we are testing on an actual infrastructure right now and trying to get it on running. I think the longest running DevNet that we have so far right now is about 5 days or like 120 hours-ish, I think. But we are working to actually do more than that. So in DevNet 3, we worked on basically trying to decouple block production and aggregation. We are trying to separate like the aggregator role so that when you're producing the block, you are not necessarily the aggregator. So we have different roles for that. And basically also creating the protocol for propagating those aggregator signatures. The things that you normally would see in this PM folder or in this document, obviously, is the objective for those DevNets, the key functionalities, and also for more recent DevNets, we are actually splitting them into what are existing, so that if you have already implemented them from the previous DevNet, you don't have to worry about this again. You are kind of like guaranteed that unlikely that there are any changes in these areas. Right? And then we listed out all the significant changes that are happening to the specific DevNet, covering the validator configs, the networking. For example, like if you're introducing a new gossip subtopic, or if you're introducing a new role that the client should implement, you can basically come to this this document and see all the changes that we are looking to tackle for each DevNet. Propose a row, all the rows, sort intervals, and so on and so on. We're also noting down like external configurations, like PQ signature is using about like 3,000 kilobytes there. I'm sorry, I think that should be 3 kilobytes. And then we are also listing down for recent DevNets the notable exclusions. For example, like we did say that we are going to work on the decoupling the aggregation for this DevNet, but we are actually excluding, say, having multiple aggregation subnets for this DevNet. So just to make sure that the scope is tight and that we are able to like deliver these PQ DevNets on time, right? I think one of like kind of like the principles that we are doing in these PQ DevNets that might be different from, say, having a next mainnet for is we are able to kind of like time box these and saying that, hey, these DevNets should take roughly about a month to implement and test to make sure that we have like a really like tight loop of feedback between implementers and researchers, which is a bit different from mainnet where you're obviously like it's mainnet, you don't want to break mainnet, so security and feature completeness is important. But for us, having this tight feedback loop, but maybe with some async features, are actually more useful as a kind of interaction between like research and implementation. So this is the first repo. We are at DevNet 3 right now. If you go into the pull request, you'll also see that we have the next DevNet coming up, which is DevNet 4. And if you're interested, you can also see the details here of what's going on or what's planned for DevNet 4. For example, for DevNet 4 right now, we are going to be focused on recursive PQ signatures. So you have the XMSS signatures, which are post-quantum secure. You want to be able to aggregate them, which we were able to do in PQ DevNet 2 and 3. And now we actually want to aggregate those aggregates as well, right? So they become recursive aggregation. And yeah, so we are looking to do this in DevNet 4, which is basically within this April timeline. So this is the first repo. That's the PM repo. You'll find the high-level plans inside PQ Intro, so you can follow this. Mostly there are like very few changes going on, right? But at least you see there's like encompassing changes, what's going on in the single DevNet. The next thing is the LeanSpec, which is the meaty one that I'll go into details. So first of all, what's LeanSpec? LeanSpec is basically the repo that we are developing an executable specification and reference test in order for any clients that want to participate in this PQ DevNet effort is able to come to look at the specification and be able to implement the clients. And not just the specifications, this specification itself comes with a lot of tests, and these tests are generated into test vectors. And clients, once they are done implementing or doing the implementation of the LeanSpec Lean client, they are able to test against this reference test, which are being implemented or integrated across all clients. So we have some sort of guarantees there that as long as you are passing the reference test, you are more or less compatible with other clients as well. So a bit of overview in this LeanSpec repo. What you'll find in this repo are mainly 3 components. The first one is the Lean consensus book, and you can see here it's called lean_consensus.pdf. This is basically if you are interested to learn about like how the PQ DevNet chain are supposed to work, how the blocks are built, how the signatures are built. Lean consensus book is like the go-to place where you can learn the conceptual level of how the spec should work. The next thing you'll find in this repo are the Python specifications. So this includes the PQ signature specifications that Emil talked about a few weeks ago. This contains all the logic for the fork choice and finality, which we are using 3SF Mini. You'll find the SSE containers for the state, block, attestations, and so on. And you'll also find the networking specs, which we expect all the clients to adhere to. And the third thing, like I said, you will find the reference test vectors, including for fork choice, state transition, signature, signing and verification, and SSC encoding and decoding inside the same repo. There are a few design principles that we have been using inside LeanSpec. First is we are using modern Python. So let's say as compared to consensus spec, I think one of the main goals is to actually kind of create this new spec so that we can experiment with all the modern Python and tooling that we are able to find. And we are able to take a lot of inspirations, a lot of the modernizations that has happened inside execution specs and bring that across into LeanSpecs to test it out and figure out what works, what doesn't work for the consensus. And hopefully, as you see in the straw map, sometime later in the next 1 or 2 forks, these specs will be merged and then combined into a modernized specs for basically Ethereum consensus in the future. The second design principle is to keep it lean. If you go into study all the specs you have in this repo, you will see that all of the specs are designed to achieve very specific goals, like post-quantum signature signing, signature aggregation, consensus is 3SF mini, and stuff like that, right? Or even let's say the networking level, it will be very minimum compared to say beacon specs, where if you go into the networking, you will see that there's the gossip stuff, there's request response, and really extensive list of them. I think you also see that the beacon chain has JSON RPC and all the beacon APIs and all those networking related stuff. You see that in LeanSpec, it's very minimal because we are not actually at this stage not trying to be beacon compatible, but we want to focus on making sure that these stuff that are related to post-quantum or new finality stuff actually work. So the consensus, the LeanSpec here is very minimal. The third thing that you'll find here is that there's no backward compatibility. So as compared to say consensus specs, you will see that all the specs are broken down fork by fork, and then each fork builds on top of each other. In LeanSpec, there's no such thing as dividing the different forks, right? So whatever you see on main, it would be for the latest fork. For example, right now we have already completed the implementation for DevNet 3, and we are building on top of that. So what you're seeing in the main branch right now is basically focused on the specs for DevNet 4. And the main reason for this is that because these are kind of like, as I said before, designed for quick iterations. We don't expect that the past DevNets are going to be revived, so we don't have any fork management or any splitting there. Yeah, like I mentioned before, we are focusing on post-quantum implementation, so there's no like beacon compatibility or beacon specific features, like there's no integration with the EL, there's no blobs, there's no validator management, so we don't have deposits or withdrawals for the validators. We have a fixed size, fixed validator set, and so on. So here's the meaty part. I'm going to be doing a walkthrough of the LeanSpec itself. That's going to include the specifications, the unit tests, test vector generation, and a bit of touch on the agent skills that we have inside the LeanSpec. So with that, maybe I'll just pause for a few seconds in case there's any questions so far.
Folks, do you have any thoughts? Do you have any questions? We don't have any in comments, but if you want to ask something in this part, feel free to raise your hand or write something. I think it's a great overview so far. Maybe I have just a quick question, like in the PM repo, whether we can find like a scheduled calls, because like it reminds me the PM repo of Ethereum, right? Where we use the issues to schedule the calls. So whether there are some these coordination efforts where we can follow maybe and join.
Right. So good question. I would say that at the beginning we intended this PM repo to serve the same as like Ethereum PM repo, but over time I'm happy to say that the calls are actually part of forecast right now. So if you look at the protocol schedule, which I think is here, you see there's PQ drop here.
Right.
So all the upcoming or all the past PQ interrupt calls are part of the forecast now, so you can follow it from there.
Yeah, right. So like regular PM repo actually. So that makes sense. Yeah. Makes sense not to split it. Yeah, awesome. And we have a one quick question in comments as well. If I understand clearly, we've write spec with modern Python, right? And why not using other programming languages?
Right. So yeah, so first disclaimer is I did not create this repo. The repo was first initialized by, I think, Toma Korachers, who's like leading the PQ consensus team right now, and also part of the CU team, which brought in experience from the execution specs. And but roughly what I remember is that it was in Python because it's the most kind of like human-friendly language, and it works across researchers and implementers as well. Someone who knows Rust or Elixir or C++ are able to read Python as well, and it works well for, say, consensus researchers. It works well for any data analysts. So Python is kind of like the common denominator in terms of language there.
Yes, indeed. I mean, that's why we have the Ethereum specs in Python as well. And we have somebody, Andres, raising a hand. So if you have a question, go ahead.
Yeah, thank you so much. My question is, so we don't have backward compatibility in DevNets. The only reason for that is because that allows us to iterate faster in that DevNets, or it is also because it allows us to, I don't know, like keep it simple. Like I think it's one of the great benefits of Lean Ethereum that we can keep that simple. So maybe not having like backward compatibility allows us to keep like, yeah, really simple, all of that. Is that also a reason?
Yes, exactly. So I think it comes from the assumption that we are not going to rewind or go back to past devnets, because the most recent devnet is always the source of truth. We don't need to like do those splits, which makes it a lot easier to implement as well, because then you don't have to worry about like having flags for devnet 0 or devnet 1, or having like, say, if you change the fork choice in devnet 3 of what was established in DevNet 2, then you don't have to kind of like do those like tricky like change management there. So you're right that it's not it's also for faster implementation as well. But I do have to say though that because we have that luxury of not having to worry about, say, oh, at this slot you have to upgrade to a new fork or a new DevNet. So we are able to kind of like like simplify that a lot. But obviously, like once we want to merge back into something that's implementable on mainnet, then we probably have to find some middle ground there.
Great, thank you so much.
Awesome. Thank you so much, guys. I think we can move on for now and then come back to questions later. Yeah.
Okay, cool. So LeanSpec. So I'll just walk through, and I think it works better if I would just walk through the code. So forgive me for being Gen Y, I think, for using Sublime, but it works best for me so far. So a few things that I want to show you. So here, yeah, so LeanSpec, you can see here that it's pretty much like a Python setup. I think one nice thing about this that Toma has been able to kind of like maintain is that for this project, because we want to kind of like keep it simple, and also kind of like want to prepare it in the eventual future that we might be doing formal verification on these specs. So Toma has been trying to keep the dependencies to a minimum. For example, you can see here we are using Pedantic for all the object models, all the types. So yeah, so there's Pedantic there. We have the lean multisig, which is in Python because the lean multisig, so basically the aggregation work is still ongoing, and those work is being done under Rust. So we don't want to kind of like turn that into a Python specs yet because it's moving so fast. So we are actually doing a Python binding here, bind it back to the Rust implementation. So that's why we have it here. And then I think the only requirements right now that we have in the spec is using NumPy and Numba, and that's basically just for like performance improvement. For example, like key generation that's been using like it could be taking like 8 hours to generate a post-quantum key right now under like plain pure Python. So we introduced NumPy here just to basically optimize that. And the rest are, I think, mostly related to the actual like validator client. One thing that I forgot to mention is that within this LeanSpec, there's the specifications part, but we also want to make the specs actually executable as a validator or as a client itself, as well as a prototypical client, not like a performant client. So you'll see all these like kind of like dependencies here that are related to the validator prototype, but it's not actually being used inside the specs. So yeah, so the dependencies for the specs are pretty minimal here. Some of other folders I want to bring to your attention that are important for this repo, I think there are, first of all, I would say obviously the specs repo, the specs folders. So you see it here in source, LeanSpec, and then subspecs. So all of the specs here, just keep the screen clean here, are related to either the specs themselves or the validator prototype that I mentioned earlier. The first one that I want to bring to your attention, and I'll just like go in kind of like logical flow so that you can see how like the specs are built upon each other. You'll see here there's a Genesis spec, and if you're familiar with the consensus like beacon chain or beacon client, then you might notice here that you'll see the config when you start the Genesis, for example. When is Genesis time? This is a bit different from beacon chain because the beacon chain you have like variable validators, but here we are fixed. So we have the number of validators here. We also have the Genesis validators, so basically the fixed set of validators that we will incorporate into each of the DevNet, and that's basically it, right? That's what you need for a Genesis of the Lean consensus chain right now. On top of the Genesis, then there are the containers. The containers, again, like I mentioned before, this is basically like the data structure, and specifically the data structure that needs to be passed around between the validators or between the nodes. For example, you see here, there's the state. So the state contains the config, the slot number of the state that is currently looking at, the latest block header, all the information related to justifications and finalization, like what's the latest justified checkpoint, which is basically the start and the block hash of the justified block, and so on and so on. You see the blocks are also in here. So you see there's block body, there's block header, and all the related stuff. This is pretty much like mimicking the beacon chain. So if you look into the beacon specs, you'll see something very similar. But perhaps all the entities here are just basically much larger with more properties because beacon chain has to do more operations, right? While we are focusing only on like post-quantum, so you only see mostly what's related to creating block, signing a block, creating attestation, signing attestation, right? So you see all the containers here. These containers are a good starting point to understand the LeanSpec because it basically kind of like gives you an overview of all the important data structures that get thrown around between clients. So if you're studying off LeanSpec, I think this is a good place to kind of like study on what we care about between clients. On top of the containers, we have the fork choice folder. Fork choice folder, again, it basically contains the logic for how to determine what's the head, what's the justified block, what's the finalized block. Basically, you'll see here there's the main class here is the store. You see the store is always governed by the time, the config, which is basically the what's the Genesis time, what's the validator set, and so on. It has the head, has the safe target, has the latest justified, latest finalized, and so on and so on, right? The media work is actually in the implementation, so maybe I can show you an overview of the implementation here. Yeah. So you see here all the methods of the star object or star class. You have the stuff that are mostly related to attestation. These are basically the entry points, right? So when the validator client receives a new block or gossip, it will go through on block or on gossip. The special case here is because the difference between like beacon chain and our lean chain right now is that the aggregated signatures, we are using ZK to aggregate the signatures because the post-quantum signatures don't have the algebraic properties that you can aggregate easily like BLS. So the individual BLS signature versus like the aggregated BLS signatures, they look the same. But for us, because they are ZK, they are different. So we have actually two methods or two entry points into the store. One for the individual attestation that got gossiped, and then we have a separate implementation for the gossip of the aggregation of those like attestation and their signatures. Then you see here, these are like the inner details, for example, like accepting new attestation or updating the heads and so on and so on. So this is where the fork choice reside. And maybe I can just like show you a bit of details on what it looks like. So within the implementation, or actually what you can see here from the beginning is that there's extensive documentation within each of the, the files here. For example, you can see the story is heavily documented, so you can kind of like basically understand how it works basically by looking at the document of each of the modules. You can also see there's extensive document on each of the parameters as well. And then you see that inside each of the functions, you also have the extensive details about how the functions work and what's expected, what's raised, what's returned. And maybe just quickly, you can see here, right? So this is an entry point for when the client gets a gossip of an attestation from another client. You need, it will be passed in the signed attestation. It needs to know the scheme. So this is a bit of like implementation details of LeanSpec. The hard thing about post-quantum signatures right now is because it's like very either compute intensive or very memory intensive. So what we do is we have a target signature scheme, and this can change between test scheme and prod scheme, right? So for example, like if a production scheme of a post-quantum signature takes like 8 hours to generate, and maybe like 500 or 1 second to sign on a very like low resource computers, we can switch to a test scheme which takes milliseconds to sign and verify, right? So this is basically a specific implementation just so that we can develop easily. And then the third one is the aggregator. So as I mentioned that we are in DevNet 4 right now, and DevNet 4 basically focus on being able to aggregate set of attestations. We are also able to specify whether this client or this instance of the client or the validator is supposed to be an aggregator or not, right? The difference is because if you are getting a gossip attestation and you are not an aggregator, you can basically kind of like process that and include that into your fork choice star, and then that's it. But if you are also an aggregator, you should be receiving the attestation, process them for yourself, but you should also aggregate them into an aggregation as well. So that's why like we need this flag inside, I think starting in DevNet 3 and then more heavily used in DevNet 4. And just to go through this quickly, you can see, we extracted out the validator ID and attestation data and the signature from the signed attestation that we received from the network. We do some simple validations in there. For example, like does the attestation target matches, a route that we have already seen. If it's not, then we probably should have raised it. If the validator ID that we receive from the attestation is from an ID that we don't know about, then we should also raise an error about that. Or if the signature from that attestation does not conform to the expected signature we expected to receive from that validator ID, then we should also raise, right? So these are like pretty simple like validations there. And once those validations happen, then we can basically kind of like finalize this and basically save it. Right? So having the signatures, if it's an aggregator, we can basically reflect that back into these are the aggregated signatures that we are supposed to be processing later on. Similarly, for say aggregated attestation, we have a set of validations that happens, and then once the validation passes, then we do whatever we need to do with that. So for the aggregation, once you validate everything that's not related to the proof itself, then we validate the proof that the proof is correct, right? And then after that, process the payload basically. Similarly, for on block, receive the block, process the signature, and basically update the state, and so on and so on. Right? So this is the fork choice specs. Next is, so you can see now there's specs for processing the attestation, processing the aggregation and the blocks. And then next thing that I want to show is the networking. Right? And you can see here there's quite a bit more of networking specifications here because you have the transport, right? So transport covers, you have to be able to cover quick, you're able to do like multi-stream and so on and so on. I think, but the most important thing that's related to these specs, I think right now, most of them are inside the gossip sub, because most of the interactions that are happening across the network right now are being done through gossip subs. There are some stuff that are being done through request response, for example, like I think doing a checkpoint sync, fetching stuff. You're doing that through request response. And also if you are missing some blocks from your state that you haven't seen yet or you missed, you can also do request response, fetching it from another client. But those are kind of like edge cases, or like not the primary path that you will be walking through. Most of the primary path are happening through gossip sub. Right? So if you're interested in how the networking works or what's being passed around, I think the easiest way is coming to this gossip sub specs. I think it's inside topic. If I remember correctly, or maybe not actually. But anyway, so you have the topics. So implementation for the topics, what the behaviors you are expecting. I'm not so sure. I haven't looked at this for quite a while. I can't remember where the exact topic is. Sorry about this. Okay, so it's actually right in front of me. So we have the topic kind, and this is basically an enum. So you can see here very quickly that even for gossip sub, we are only having 3 types of gossips: gossiping the block, gossiping the attestation, and then gossiping the aggregated attestation. So that's basically like the 3 main gossip subtopics that we are disseminating across the network for the Lean consensus chain that we have right now. So that's networking. We also have the SSE. One nice thing about this over, let's say, like Beacon chain is that for the Beacon specs, right, the consensus specs, you'll see that, let's say, for the SSE, we are using the remerkleized client, which remerkleized library, which is basically the SSE library, I think, created by Proto Lambda. And that's a very a full-fledged SSE library. And the thing is, because our LeanSpec, we try to be very minimal and try to have as least number of dependencies as possible. Thomas actually recreated the SSE implementation inside this the spec itself. So if you're interested in the kind of the minimum specs of the SSE that is required for LeanSpec, then this is the folder to go to. And some peripheral stuff like metrics. So if you're interested in what kind of metrics that we are emitting, then you can also come here. And if you're familiar with either Prometheus or like Grafana, then you can see these are basically the parameters and the setup that's needed to basically for Prometheus to consume from these clients, and to be presented on Grafana. So you can see all the metrics here related, say, node information, all the fork choice information, all the state transition, so on and so on. All the metrics are here. So those are mainly the client specs. As I mentioned, there are also other specs related to, not related to clients. For example, we have the XMSS. So this is basically what Emil talked about a few weeks ago about how the post-quantum signatures work. So you can also find here basically the full specs in Python of how the post-quantum signature works. Because we try to reduce the dependency as well. Some of the dependencies of XMSS itself, for example, like the Poseidon 2 hashing, we should be changing that to Poseidon 1 because the Poseidon 2 security has been created. But basically, the components like the signatures and its dependencies like Poseidon, and like Bear, which is the prime field used by the signatures, and I think the aggregation part as well are also here. One note, again, aggregation is not here yet because that's still fast moving. What I believe is once that's stabilized, then we'll also port that aggregation specs into Python as well. But for now, it resides in LeanSpec. And then, as I mentioned, there are some of the client prototypes that are not related to specs, but important to actually have this LeanSpec as something that is runnable as a client. For example, storage. Right? We don't want to specify or enforce the storage that each of the client implementation needs. That should be up to the client itself to decide. But they reside in this specs because it's basically being used by the prototype client. There is pending discussion that we want to make this distinction clearer on what's the specs that the client should implement and what are the other kind of glue implementation that we needed for the prototype client. But that's still to be done, right? But as long as you know that this subspecs folder contains both the client specs and also the prototype implementation, and the important folders for the client specs are the containers, fork choice, Genesis, networking, and so on, then you should be fine. So those are the specs part that you can find. You can learn about this by yourself. Before I move on to the test vectors, which are also part of this client, maybe I'll open up for some Q&As at this moment. I think there are...
Indeed, folks. Yes. Here's some questions in the chat. The recent one, is there some info on which Snark's proving systems will be used for aggregation in the further devnets?
Yes, so it is not part of LeanSpec, but you can definitely follow it up to date to the latest, the latest work that's going on. That would be in the Lean multisig folder. So actually, if I remember correctly, no one has introduced Lean multisig yet, so maybe I'll just mention about that. So this is where the meaty work of the aggregation that's happening right now. If you're interested to know more about this, you can go inside this minimal CKV and PDF. This should be basically the book. I can't remember, so I'll have to download it quickly. Show here. Yeah, and so this is very extensive, right? So you can see what's the goal of the CKVM, and again, this aggregation is using ZK. That's why it goes into pretty quite a lot of details on how it works behind the scene. So the specification of the VM itself, what field it's used, what's the memory structure, the registers, and also how the proving works, how the aggregation works. Right? So you can read the kind of the human explanation in here. If you want to go into details, obviously the implementation is here. Note that it's happening really quickly. The commits are basically coming through multiple times a day, so it's very fast moving. And I think the nice thing about this repo is that MAO has also been keeping track of the performance as well. So there's some benchmark here. One thing that I want to bring to your attention is this like really fancy benchmark here. Basically, it's a one single benchmark that you can run. You can basically clone and run it yourself. I think this is also like a kind of like a good starting point that you wanna, if you wanna kind of like look into how this lean multisig work. But basically, this benchmark a few things, right? So at the first level, it's benchmarking the number of signatures that it's able to aggregate per second. So you can see here, it's able to do right now 800 signatures per second. I think this is on the M4 Pro MacBook that he's running. It's being fed in 1,400 signatures. So it's taking about less than 2 seconds to aggregate this. The nice thing about this benchmark is that MAO also did an aggregation benchmark. So once he's done with these like 1,400 benchmark 3 times over, he did an recursive aggregation of these 3 aggregations. And he's also doing some additions and removals as well. So here you can see that he's adding 25 more new signatures, and there are 10 duplicate signatures. So the lean multisig is actually able to handle like all these like new signatures and duplicate signatures within the proof itself as well. And it is taking about 1.2 seconds to aggregate all these like almost like over 4,000 signatures in the aggregation. And the proof size is actually gone down from 350 kilobyte each. It becomes 310. That covers all the 4,000 signatures inside it. He's also done aggregation of aggregation, so that you can see here that's three recursions happening. And you can also see here that the lean VM or lean multisig right now is not only doing like merging of aggregations, but it's also able to do recursive aggregation on top of itself. And what you get from that is actually a reduced overall aggregation size. So it went down from almost 300 kilobytes. If you do a recursive aggregation on itself, you are able to reduce that down to 129 and then 124 kilobytes. So really cool work being done here. Really interesting. If you're interested, go check out this repo, go check out the PDF, and then go read the code base. It's really cool. That's a long answer to the question. But yeah, basically go to lean multisig, and then you'll find out all the latest stuff on the CKVM.
Yeah, that's awesome. Thank you so much.
Yeah. Any other questions, maybe?
Yeah, any thoughts on this part, folks? Hope you are catching up. I see a lot of sort of overlap with Beacon Chain, and like what I'm wondering about is like generally maybe like high level like efficiency, like are we like we're doing a bunch of stuff that has been done before and even like as the spec evolves, maybe is a bunch of this going to be rewritten as well? Like how do you see it like from the like long-term perspective or like from the efficiency?
Yeah, that's a good question. I think we mentioned this briefly, that like the overall goal of LeanSpec is to iterate quickly. So yeah, we skipped a lot of stuff that should happen on Beacon Chain, but we don't have it here. So yes, eventually these two kind of like worlds need to merge somehow. I don't think there's a concrete decision on anything about that so far. Just because like even like just for the LeanSpec itself, you can see like there's a lot of development going on. There's going to be a lot of changes, a lot of improvements happening to the lean multisig itself. So that's going to get faster. But also one thing I want to point out, for example, like the individual signatures, like before the aggregation happens, it's about 3 kilobytes right now. That's big, right? That's big compared to I think a few like 50. I don't remember exactly, but yeah, less than like 100 bytes for BLS signatures. So so what that means is that the networking is going to be heavily affected because of this large signature size. The other thing to note is that for example, the benchmark that I just showed you, we are able to do 800 signatures per second. As I think all of us are well aware, we have 900,000 validators on mainnet. So being able to, let's say, if you want to aggregate the entire validator set on mainnet right now, that is going to take ages, even though we have aggregation in place. So it's important for us to also experiment on the kind of the aggregation layer model. How many aggregators do you want to have? How big of the subnet size you want to have in those aggregation subnets, and so on, right? So there is still a lot of work that, let alone not having to kind of bring in the beacon features yet. There's already a lot to experiment with. So I guess it's going to take probably quite some more time before we settle on all the LeanSpec features, and then only then we'll kind of realize how much work, which way should we go? Should it be LeanSpec merged back into consensus spec? Is it consensus spec merging here or somewhere in the middle? I think that's undecided, but I guess you can see the kind of the requirements, the different requirements on both sides, that we want to keep it separate for the time being.
Got it. Yeah, thank you so much. Yeah, thanks a lot. Oh, I think we have another half an hour to go, so let's continue for now. And yeah.
Cool. Okay. Yeah. So I just mentioned about the specs being inside the LeanSpec folder. You can obviously see there are many more folders in here. What I want to bring to attention as well, as I mentioned before, is that the LeanSpec contains a spec, but also contains the reference test that all the clients are using right now to test, to make sure that, hey, we are actually passing the same tests that are generated from the LeanSpec itself. So we should be more or less compatible with other clients, right? Where does that reside? I'll just maybe close some of my tabs here. Where's that? So in terms of tests, we do actually have two types of tests right now. We have the unit test, basically residing in LeanSpec here. I won't go into much details here, but just for you guys to be aware, you can see here that the structure is pretty much the same as the specs, and this basically contains the test that we want to kind of test to ensure that the specs are behaving correctly, but not necessarily the test that we need the clients to actually do, right? So for example, recording metrics here, it's not super relevant in order for clients to check that, hey, my fork choice is correct. You don't actually have to test metrics recording or storing stuff like that, right? So these are basically unit tests. I think if you're not doing any stuff like implementing or changing stuff on LeanSpec, then you probably don't need to worry about this folder. The folder I want to bring to your attention is inside test/consensus. And in here, you'll see that there are mainly 4 folders. So there's the fork choice folder, there's the SSE, there's a state transition, and there's the verified signatures. And these 4 categories of tests are basically the source of truth of the tests that we are generating for all of the clients. And I think we have about 8 or 10 or even more clients right now that we are going to be enforcing all the clients to test against these test vectors to ensure cross-compatibility across all clients. I'm going to show some examples here, so maybe just see how it's structured first, right? So we can see here for the fork choice, it's kind of categorized into different areas of tests that you want to test. For example, these are the set of tests that we want to test in order to check that that our fork choice is actually determining the head correctly. We have the fork choice reargs to do with the reargs. We have the lexicographic tiebreaker. So this is the case where you have 2 forks, 2 blocks, and 2 forks of equal weight. How do you figure out between them, right? We want to use lexicographic order. So basically, if the fork hash starts with A, that should be like the fork choice that you pick over fork choice that starts with B, for example. So these are the tests that happen. I want to go through one of the tests maybe. I think the easiest to understand is probably maybe the tiebreaker, I think. So what we do in these tests, let me give you an overview. Oh, there's only one test right now, so that's easy. So for example, like what this test does, it is expecting that the fork choice should select the lexicographically highest branch when the weights are tied, right? So if two forks have the same weight, it should select it by the block hash, whichever one is like higher in terms of the alphabetical order. Another interesting thing that I want to point out is how we design this test. So we want to make these tests reproducible, but also easily extensible, right? So we want to be able to create new test cases with ease and make it easier for anyone to understand and also update these tests. So you can see here that all these are kind of like the steps to test are encapsulated inside kind of like helper entities here, right? So in order for us to define a test, we obviously need to create the test function and name it accurately. Like for example, test equal weight should use lexicographic tiebreaker. You can see here that once you get into the function itself, you define it that this is a fork choice test, right? So this is how basically the framework knows that this is a fork choice test. It needs some specific tests. It needs to do some specific behaviors. For example, like calling the fork choice when this is being performed, as compared to like SSZ, which has its own test implementation and test fixtures. So you define the fork choice test, then you give it the steps that you want to happen inside this specific test case, right? For example, like in this test, we want to create a common ancestor. So basically a block that the forks that we will be like spawning out should base on, right? So we create this block step. And inside this block step, we basically have a block spec. So basically, it's a specification on how you want the test setup or the test fixtures to create this block, right? And we are able to define, say, this block should be SOT1. And we are also able to kind of like tag a label. This is only a test label, so it's nothing to do with consensus, but it just makes it easier for us to refer to a previous block, right? So you see this a bit later on. We are also kind of like doing a check to make sure that the block is being created correctly in this step. So this is basically an equivalence check that the head slot for the store right now should be SOT1, and the head root should be base. So basically this block, because it's the first block that we create. Then we move on to create the first fork, right? So we create the SOT. We assign it parent label. So the test is able to kind of figure this out that, okay, so this block should be based out of this block, right? So the block parent would be based out of the block hash of this parent without us even having to kind of like doing that logic inside. And then we do the check again. I'm going to speed up a bit more because there's quite a bit more to cover, right? So you create the fork here, and then on the same fork, we create the second block here, and then we attach an attestation to it, right? So now the fork A has a weight here, and we check once more within the same step that it's still correct, that it's still pointing to fork A, and it should be SOT3. Now, right, what we are doing next is introduce fork B in SOT4, right? Notice here the parent label here is base, so this block is not actually basing out of SOT3 or 2. It goes back to SOT1, which is the base, which we label it here, right? So the parent label is base one, the base here, and we label it for B4. Similarly to fork A, we created another block for fork B. We add an attestation to this fork, right? So there's also one attestation here. So you can kind of like see here that at this point, we should now have two competing forks, and the fork should have a weight of 1 each because we added one attestation to fork A, and then we added one attestation to fork B. And so instead of checking let's say like the root label corresponds to one fork, which we can't right now because we don't know what the hash is. Like it's not yeah, it's not really, well, it's deterministic in a way in this case, but it's really hard if you want to kind of like put the logic in there to check the hash. To make it easy, we have this helper to say that, hey, here for the store, let's check that between fork 3 and B, the store should actually be the head that chooses among these two in its alphabetical order, right? So in this way, we are able to test that after doing 2 forks, adding 1 weight to each. This basically determines that at the end you should be choosing between fork A or B, depending on the alphabetical order of the block hash of these 2 forks, the head of these 2 forks. So that's in general on how it works for a test case, right? Similarly, if I go into SSE is a bit tricky, it's a bit different, but you can see here there's a SSE, and then you have the type and the value on how it should like transform between like the native object and into SSE. State transition here, similarly, you can see the change. Yeah, so start with like state transition test. You have a pre-state. You have no blocks here. Let me show. Oh, this is Genesis. So you don't have any blocks. It's basically asserting, that the Genesis state should look like this. For the ones that are processing blocks, you can see here that you'll be inputting the pre-state, right? And this is basically the pre-state that we are specifying. Now we have a block, and here you can see that we are using the same helper blocks spec, and we're basically adding slot 1, and we are expecting that after applying the state transition to the blocks that we're given here, this is the state expectation that we are expecting after processing those blocks. You can see here the state should be now up to slot 1, latest block header, and so on and so on. Right? So this is how we are defining the test vectors for the clients to be able to consume. Now, I guess like the kind of like last question here in terms of how these test vectors work is that, but how does it actually generate an actual test, right? So basically that belongs to, I think, package. Oh wait, I already have this open. It is inside SRC and consensus testing here. Yeah. So you can see here that there are test types, right? So for example, the block spec that you see previously, it's basically defined here, right? So if you're interested in what the block spec can do, you can see here that you can do the slot, you can input, yeah. So the label is also here. And this is basically kind of like the data structure that we are using for the test vectors. The logic on where the test execution happens, for example, is inside the test vectors here. You can see there's files corresponding to the folders that you see before, the 4 folders. You can see there's the foresight test resides here. This is the name of the test fixture itself. And if you want to see how it processes those test cases, the logic for that resides in the make fixture, right? So it does all the basic configuration validation. It sets up some keys. You can see here it sets up all the validators, set up the state, and so on and so on. And what I want to bring to your attention as well, you can see here that there were the steps that were inside these test cases for the so you can see the steps here, right? So if you go into the fork choice under the fixtures, you can see that these steps are being enumerated in here, and it's basically matching whatever that you're defining, right? We have defined the block step, so this is what the block step would do, right? So it would process the test one by one, right? So whatever it sees, if it sees an attestation, it does the attestation, and so on and so on. Then at the end step, what it does is there's the framework. So basically these test vector framework, and the main file I think resides in the filler.py. I think. So in the filler here, you see that there are methods for adding the fixtures and so on. And I think you can see here, yeah, so you can also see here how the test vectors, once they are generated, you get like basically the pre and the post response objects out of that. And it's basically converting this into a JSON format and then save it to a file. So this is the main kind of like orchestration level of the test vectors. And if you see here, or maybe not, actually, I think it's hard-coded somewhere in the, oh yeah, fixtures, layer format test path, right? And so once you run the test generation, the command is inside the README. You can see that there are fixtures folders here. Once you generate them, then basically whatever test that we created, for example, like we looked at the tiebreaker here, if you come in here, you'll see that there's this now becomes a JSON file. And if you look inside this JSON file, you'll see that there's the anchor state, the block. So these are basically like kind of like the initial state that you start off with. And then you have the steps, right? So this is basically the steps that you see here. Block step 1, sort 1, 2, 3 gets converted into, it's basically capturing all the details of each step of what it was performed on the specs, and basically translate this into a JSON format, right? So the step, this is valid, it's a block, step type is a block, it's for slot 1, and so on and so on. And then you have the specs for slot 2, and then you can also see that the parent, the parent root of slot 2, of block 2, is slot 1, block 1, right? And so on and so on. You can also see there's the check in each of the steps here. And so these checks are basically what we define here, right? And then you can see, I guess, the last step that the check, it's a lexicographic head because we don't know exactly the hash here. So this is up to the client to check it for themselves. So all in all, what we have just seen in these test vectors is that for this LeanSpec, we are able to define each of the tests in different areas using kind of like almost like human readable steps, right? Each of the steps here, the checks that need to happen. This gets tested by the test vector framework here, and then gets filled by the framework itself as well into JSON file. And so we arrive at the test vectors on the initial state, what needs to be applied, what needs to be checked, and what's the post state. And we are able to basically rest assured that these test vectors are actually conforming to the LeanSpec because we are using basically the LeanSpec itself to generate this. And so when it's in JSON, so all the clients are able to process this and basically generate tests that conforms to the LeanSpec itself. So these is the LeanSpec part. Again, pause for maybe any questions. Okay, if not, then maybe I'll touch on a bit of the code base, which is the last part I want to show. We are experimenting a lot with the AI agents as well. And so far, I think it's been useful if your engineering skills is like really strong, like AI can be really useful to you. There are a few skills. Some of them are very obvious, like for example, like running checks, right? These are very easy. We just like telling the AI to know what command to run. But the more interesting ones that I want to show you, and I think like we are making pretty good use of AI, is, for example, the client test. So the thing with like developing or like creating the specs here is that obviously like sometimes you change something in the framework and you might actually want to test with the clients that they are still conforming because you're actually testing something on the lean side that's not like really like specification focused. So there should not be anything that's changed on the client side, but you want to make sure that there's still compatibility there. And you don't want to actually, like it's actually quite tedious to clone the client, keep it up to date, pull the latest changes, and then run or like copy over the test vectors there and then run the test vectors inside the client, right? So I think that's something that's really like tedious manual work that AI can do. So we have this client test skill that basically we are defining that, hey, you should be able to, and for us to just like tell you to client test against a client with a client name, and then it should be able to do that, right? So we are able to define it to say that when we say, hey, AI, you should like test Ream for me, what it would do is it would generate the test vectors. This is basically the command to generate the test vectors that you just see. It should be able to clone the client. And if I remember correctly, the clients are defined here. So we have the link to the repo of each client. So the AI knows where to clone it, right? So it clones the client. It will sync the fixtures, right? Because the old fixtures might be out of date. So it would copy the fixture that was generated here and put it inside the client and then run the test against it, no matter what the client does. And because like all clients have like different commands to actually run the clients, this skill has been really useful for me to kind of like change stuff on the LeanSpec. And I would say like, does it necessarily need AI? I would say no, because you can actually write scripts to run all these stuff, right? But imagine like the lines of scripts that you have to do to actually cover all the clients and to actually maintain this script. Being able to write this in human language and within like say like less than 70 lines, I think has been like really useful for me in exchange for the tokens that you have to bring. Another interesting skill that was proven to be useful to me as well. For example, like if you want to check the diff between different devnets, like I said, like we are not actually maintaining like a flag that you're available to switch between like devnets easily. All you have is the commit history. So one useful thing that I've been using so far is this skill called SpecDiff. So instead of actually combing through all the commit history by yourself, this SpecDiff is able to figure out the diff between devnets because we have defined the latest commit for each of dev here. And the skill is basically able to figure that out, which commit that it needs to diff against. And the thing is, instead of actually having to review the Git diff, line by line to see what changed, we are able to use AI here to kind of like summarize those changes for me to see as well. Obviously, AI can be inaccurate at times, so you have to use this at your own risk. But for like simple like diffing, seeing the overall changes, this has also been useful. And I think if you are interested to see like the changes between the devnet as well, I think this is also one way to get up to speed on the changes that we have per each devnet. And yeah, so this is the LeanSpec part. The walkthroughs, so when we went through the specifications, we touched on the unit test a bit, we touched the vector generation and the agent skills. Maybe I'll just speed run through the rest and then leave some maybe like 5 or 10 minutes at the end for Q&As and discussions. So we have lean metrics. Go over this quickly. It's another repo, but basically we are establishing a shared set of metrics early, and this has been proven useful so far because we now have a shared Prometheus, we have a shared Grafana, and I will also explain a bit later on. We also have a shared Jupyter notebooks that crunch all those metrics and give us some kind of informative insights into how each of the devnets are performing. So if you're interested in the metrics and what are defined, this is the repo to go through. I'll skip these. Lean multisig, as I mentioned earlier, this is where the CKL aggregation happens. Go follow it, super cool. And maybe actually to answer Shivam's question a bit earlier on what kind of like stacks or what system is being used. So this is the overview, right? We are using WHIR, with WHIR, as the polynomial equivalent scheme. We are using lookup star to do some lookups. We are using Super Spartan to do error constraint. We're doing, again, lookups for lookups. But this is as of January 2026. A lot of change since then. So this is definitely inaccurate. If you want to check for real on what's going on right now, check out the lean multisig. But if you are just curious about lean multisig and just want to know more about how it works as of January 2026, so 3 months ago. You can also check this YouTube link, which I also shared under Ream Study Group a few months ago. And then last two parts in terms of infrastructure and tooling, we have Lean Quick Start. So Lean Quick Start is basically Ansible and Bash scripts that we are using to quickly spin up a multi-client PQ DevNet. So we are able to basically clone that Lean Quick Start, run a few commands, and you're able to kind of basically recreate your own DevNet inside either your local machines, or if you have some remote servers running, it's built out of Ansible. So it's quite easily to kind of like run that and make it set up your remote servers as well. And then last thing I want to talk about is PQ DevNet Observatory. So this is like kind of like the latest addition to the overall stack. And the main goal for this is that we already have the infrastructure to run the DevNets. We already have Prometheus, we have Grafana to collect and display the metrics. This latest addition helps analyze the metrics. Right, so basically you can see here in the Lean Roadmap, observatory.leanroadmap.org. Once you go in there, then you can see all the kind of like analysis for each of the DevNets. But mind you, though, that we are actually not kind of like screening out any of DevNets. Some of the DevNets didn't work, last for like pretty low hours, like maybe 30 minutes, sometimes even like 15 minutes or even less. So you might have to be a bit careful on like picking which notebooks you want to see. But basically, it kind of like breaks down the performance of each of the clients in terms of the PQ signature, signing and verification, PQ aggregation, consensus, like how many slots it processed, what's the head slot, did it get to finalize all the way through. You can also see some of the networking, how many attestations received, I think we have that, not sure. But yeah, peer connections, we have the network throughput and so on. You are also able to see the resource utilization of each of the instance, right? And we're running basically just one client per instance right now. So you are able to see pretty clearly on the kind of like how resource intensive PQ signatures are using, and also the difference between the clients. Right? So CPU, memory usage, and so on are also residing in here. So if you're interested more on the performance side or on the actual behavior of the DevNet, you can also look into these Jupyter notebooks. This was created only a few weeks ago, so there might be a lot of bugs in there. And also, I think these are still like very basic metrics. We haven't done any kind of like more complex, metrics yet. So if anyone is interested, this is also for data-heavy users to work on as well. And yeah, so with that, I think that's so that's basically kind of like the everything in my talk. Recap again, we talked about the coordination level, like we have the PM repo, the specifications level, we have LeanSpec and Lean metrics. Shared implementations, we have LeanSig that Emil talked about, and then Lean Multisig, which we just mentioned today. Client implementations, Kobe already talked about this maybe a week or two ago. And then infrastructure tooling, which I gave an overview just now. So hopefully, with this kind of like picture, like basically everything about the Lean consensus effort right now. And if you're interested in any specific areas, then hopefully you can deep dive into that. And if not, you can also like see the relationship of like all these repos working together to actually create the Lean consensus and PQ DevNet effort. Some links to resources. These are the ones that I mentioned. And then if you're interested, I'm working for Ream. Our Telegram is here, and you can also follow our X or Twitter here as well. And yeah, that's basically it. Thank you everyone for staying until the end, and happy to take any questions or just like discussion in general.
Awesome. Thank you very much. Very well. Yeah, lots of great resources. I think a ton of stuff people can study further and exercise. Okay, we have one question in the chat now, but meanwhile, folks, feel free to raise your hands or prepare some more questions. We have a couple of minutes to go. I see no release or versioning in the Lean multisig repo. How do we keep track of the latest changes?
Great question. I think I missed that part. So Lean multisig right now doesn't track changes because it's fast moving and most of it is experimental. Like I mentioned, like probably half of the diagram that I showed you on Lean multisig is probably obsolete right now. But how do we do that in terms of PQ DevNet right now is the PM repo. So one thing I forgot to mention is that inside each of these like high level documents, maybe PQ DevNet is more stable. You can see here we have the specification targets. So for whichever PQ DevNet that we are working on, we will be updating this document, right? So you can see here specifically which pin. It's basically a pin comment of what should be referred to for each of the whatever dependencies that we depend on.
Okay, very well. Thank you. Yeah, some more. Got it. Folks, do we have any more thoughts, more questions before we wrap up here? We have a few more minutes space if you guys want to ask about something. I know it's been a lot. It's a lot of resources, a lot of things. I think you also pointed us well to where to follow up to learn more. But if you folks are unsure about anything. Yeah. Okay, I don't see many people asking, but we already had a couple questions, so let's wrap it up here. I think. Okay, Huang has a hand up. You want to say something? Yeah. Don't hear you. No, we don't hear you. Or is it just me?
I just trade my mic. Can you hear me now?
Yes, it's so good now.
Okay. First of all, thank you so much for your sharing today. I want to ask, maybe this is not really related to like Lean right now, but what brings you to working on like LeanSpec and like Lean Matrix consensus in general, or like how is your background that leads you to this part? So
Sure. So my background, just to go through quickly, like my background has mostly been about like technical. So I graduated computer science. My jobs has always been technical. I started working in Web 2 actually. I think my first job was in 2012. So it's been quite a while. And yeah, since then my background has always been backend. I also did some banking work, like actual like real nasty TradFi banking work, and yeah. So So with that, like I got interested in Ethereum. I worked on a couple of projects in Ethereum back since 2017 as engineers, and have always more or less worked with Ethereum since then. And just kind of like, yeah, for full transparency, I started becoming interested in Lean effort and also Ream back in DEF CON in Bangkok. So Justin, made this like announcement of the Beam chain back then. That's what it was called. And I talked about like post-quantum, talk about like big different changes on the consensus level. And because I have always been in Ethereum, my background has always been backend. So, yeah, Lean consensus just feels natural to me, as something that I would be interested in. So I joined Ream back then as a coordinator, but also with my background as engineer. But my background has never been Rust actually, and Ream is doing Rust. So thankfully for them accepting me to join. But my background was in Elixir, and back then shamelessly of PHP. So Yeah, so that's my background. So mostly right now I'm learning Rust with Green Team, but I'm also doing a lot of LeanSpec, which is in Python. But I guess like my biggest contribution, surprisingly, is actually on LeanSpec, and I'm doing Python right now. But I think it's mainly because that back experience where I work in TradFi banks. Hate to say this. And then it gets really meticulous when you actually want to implement something inside the bank. Right? You go through like a lot of process, and then the steps are like really detail focused. So those are kind of like the quality side I was able to kind of bring over to Lean Consensus and LeanSpec and Read.
Thank you so much for the sharing. So just to quickly summarize, you previously have experience working with banking, and then like you interested in Ethereum to the point that you get to work with LeanSpec, right?
Yep.
So do you have any like suggestion or advice for people like us to begin working on LeanSpec? For example, like myself previously, I'm working on like client generation. It's similar to the LeanSpec in a way that we also have like fixture for like correcting generated the client, and also that you have to versioning the like many test vector so that you make sure the query work, or in this case the behavior of the client work. So yeah, do you have like any advice for beginners like us to quickly fast track this?
Yeah. So I think so. My thinking when I started Lean and Ream stuff is to kind of like figure out where would I fit in with the most value that I can provide, right? So with my background, in banking, I also did a lot of like extensive programming, even though I didn't do Rust, and a lot of like managerial work back then as well. So I kind of like offered that maybe I can do coordination and also like do some specification stuff. So I think that's how I start. So I would say like my suggestion would be like figure out what's like your best or the most value added thing that you can do, and try to jump and prove yourself there. And another thing is that before actually like properly joining Ream or actually any projects really, I think open source contribution really helps a lot. Like being able to prove, basically able to work on the public repos, being able to just basically like send links to whoever you want to work with, and basically it's a link to the pull request page filtered by you as an author. I think that is super useful to prove yourself. And yeah, I guess the rest is just like basically pursuing your interests.
Okay, thank you so much.
Awesome. Thank you so much, guys. I think it was a great way to finish the talk. Thank you so much for the overview. It's very inspirational to hear your journey as well. So thank you so much for sharing all of that and all the technical resources for the Lean, for the spec, for DevNets and tooling. It was great. Yeah. Awesome. So let me stop it here, and thank you so much everyone for joining today.